Hi, in this tutorial we are going to solve a question related to radical reactions. The question asks us, draw the organic products formed in each reaction. Let's start from the first option. The first option has an alkane reactant, chlorine molecule, and light. So basically this will be radical chlorination reaction. And if you look at the alkane, we have a couple of different positions. So we have this position, which is a tertiary carbon having one hydrogen. And here we have a primary carbon having three hydrogen. And we have here another position, and since the molecule is symmetric we have two of them, and these are secondary carbons having two hydrogens each. And also we have the fourth type of carbon, which are primary carbons again. We have two of them and they are equal and symmetric, and each having three hydrogen. So basically when we have radical chlorination, we are going to obtain a variety of products since chlorination is not selective that much. So let's draw each product. Let's start from the A. So if we abstract a hydrogen from A, and a chlorine will be substituted there. So that's the first product. And the second product will be B position. And the third one will be C position. And you need to just draw one of them because it's going to be the symmetric molecule, same. And the last one, if we abstract a hydrogen from position D, that will generate another chlorination product. I'm going to draw this way. Okay, we have four products. And let's move to the second option. In the second option, again, we have a radical halogenation. In this case, it's the bromination. And bromination is known to be very selective in terms of position. So if you have secondary or tertiary carbons having hydrogens, and the substitution bromination will exclusively occur in that position. Let's look at, we have here a tertiary carbon, and we have here a primary, and it's primary, and these are all secondary carbon. And again, bromination will be exclusively for the tertiary position. So let's draw the product. And if you ask here why there is no reaction over here, because this is a quaternary carbon, it doesn't have any hydrogen, so there is no reaction in that side. But in the tertiary position here we have one hydrogen, so the reaction almost exclusively produce this bromination. Let's move to the third option, option C. Option C is not a radical reaction, it is a polar reaction, hydrogen bromide addition to alkene, and we know that it follows Markovnikov rule, meaning that it will go through a carbocation intermediate, it will produce more stable carbocation, and then the bromine will be attached to more substituted carbon. So basically, this carbon is a tetrasubstituted carbon. This carbon is monosubstituted carbon. So hydrogen will be added to less substituted carbon, and bromine will be added to the more substituted carbon, which is a Markovnikov product. So let's draw the product. So bromine will be attached to more substituted carbon. Let's move to the option D. Option D, again, hydrogen bromide addition, but in the presence of a peroxide. And when we have peroxide during the alkene addition reaction, the reaction proceeds through a radical intermediate. So for that reason, it's not going to be Markovnikov addition, it's going to be non-Markovnikov. Okay, when you see peroxide, so the reaction proceeds through radical intermediate and the product will be non-Markovnikov. So basically this is less substituted carbon, this is more substituted carbon. So bromine will be attached to less substituted carbon in this case. Let's draw the product. So bromine will be attached here and hydrogen attached here. So, but you don't need to draw hydrogen in the skeletal structure. Let's move option E. Option E, bromine addition to alkene. And this is not a radical pathway, but this is again a polar pathway. And the product will be dihalide. So halogen addition to double bond. So let's draw the product. So you need to add bromine to both sides of the double bond. Let's move to the last option. Last option, again, bromine addition in the presence of NBS and bromosuccinamide, but in the presence of light. Again, this reaction is going to be through a radical pathway. Okay, and we know that when we have alkene and when we have NBS and light, the addition or bromine halogenation will take place at allylic position. So this is the allylic position, this is the allylic hydrogen. So again, the first step it's going to be the generation of the radical species, and the radical will be forming exclusively at this allylic position. Let's just draw the intermediate, then we can guess what's going to be the product. So this is going to be our radical intermediate, and we know that when we have allylic radicals, they can undergo like a resonance transformation. So instead of radical position here, you can have the radical position here through the resonance. Let's draw the resonance. Basically, this unpaired electron shifts to here, and from pi bond another electron shifts to the same bond, and we form the pi bond. The other electron at the pi bond shifts to this carbon or stays at this carbon. So that's the reason why we can have two resonance forms for this radical. So then the next step, bromine addition. So bromine will be added to either this position or that position, because we have a resonance form. So basically we are going to have two products. The first one will be bromine at this position and also bromine at the other position. Again, the reason is resonance. Thank you so much for watching the video.